All right, so welcome back everybody, or the four of you who are here. So today's tutorial is going to be nothing crazy. We're not going to really, do anything too complicated. We're just going to go over the assignment, and any questions you guys have.
We switched apparently.
Yeah, we switched the rooms. So this is for 3SO3. So we're not going to do anything crazy. We're just going to do go over the assignment and do some related questions, so you guys can get an idea for the assignment. So the first thing I want to talk about is control flow graphs. So you guys have seen those in lectures? Yes? No? Yes? Yeah. So there's a question on your assignment about control flow graphs. So essentially, what it is it's a graph, and it basically models sort of the flow of your program. So you have states that are represented by nodes, and then you have transitions between nodes, and then you might have some condition. So we're going to do a quick example of a control flow graph. We have a binary search example. So your typical binary search, searching for an element. And we're going to try and figure out the control flow diagram for this. So typically what happens is, statements are represented by nodes, and arrows represent transitions between going from one state to another. So for example, this is a statement. So this will be represented as a node. This is also a statement, so that would be another node. But these conditionals will be represented as arrows, and these would be your sort of conditions to transition, where you have key is less than A at mid, key is greater than A at mid. So it's always useful to sort of label these. So this would be, that would be one of our nodes. That would be another node. That would be another node. This is also a statement, so that would be another node. And this is also another statement. So in total, we have 5 nodes. So anybody know what sort of the control flow graph is going to look like? Anybody online? Any ideas?
It's going to start at 1 and split to 2 and 3.
Yeah. So we're going to start at 1, and usually you have like some initial state. We'll just call it 0, and then from 0 you're going to go straight to 1. Let me make this higher actually. So typically you have like some starting state, we'll just call it 0, and then you have 1, and then from 1 you're gonna, as you mentioned, you're gonna branch off to 2 and 3. You can go to 2. You can also go to 3. So what are the conditions for going from 1 to 2 or 3?
If the key is less than A mid. So
basically, if the key is less than A mid. What about the other one?
And greater than.
Yeah, if key is greater than, right? And there's actually another one that you can go from 1. Sorry?
The else too,
like down here, right? Yeah, so node 4. So that's key greater than A mid. And you can also go from 1 to 4, which is this else right here. So this would look something like you go to 4. Now you don't always have to label every single transition, so it's sort of implied that this one is key equals mid because this is less than, that's greater than. So it's implied that that one would be when key equals mid. What about the 5th state?
I guess they would all go to the 5th.
Would all of them go though? Or
would it only be like 2 and 3?
So 2, 3, yeah. So you'd have like node 5, but because node 4 returns, you would never go from 4 to 5. But you could go to 5 from 2 and 3, right? And there's one other thing that we're missing. There's one last thing that's left.
Like a formal end state?
Yeah, sure, you can always add those in, but there's like another crucial part that's missing. I mean, we do have a loop, right?
Yes, like 2 and 3 go back to 1.
Yeah, so you can go back to 1 from 3 or 2. And what would be the condition for that?
Like I guess as long as low is still less than.
Yeah, this is condition, right? Basically that. Yeah, so you can go from 2 to, it's kind of messy. You can go from 2 to 1 if low is less than or equal to high. And this one was, we'll just call it K is less than A mid, just to save some space. Or that one was greater. Sorry. And then same thing for 3, right? So we can go back to 1 as long as low is less than or equal to high. And this one was k is less than a mid. All right, so any questions? So typically you have a starting state, and then statements are represented by nodes. So each node here is a statement. So where you compute mid, where you can assign high equal to mid minus 1, low equals mid plus 1. So anything that's a statement is usually a node. And then you have transitions, and sometimes you have conditions for those transitions, like in this case, but sometimes you just go straight to a certain node without a condition. So any questions? Should be pretty straightforward. Anybody online have any questions? I don't see any messages. Cool. Yeah, it looks like no questions. So we'll do another example now. So instead of going from taking code and translating it to a control flow graph, we'll do the opposite. So let me erase all of this. Very enough. So we basically have this example. We have this node here. And 1, 2, 3, 4. And we have 5, 6, 7. Okay, and then because we don't have the code, we only have the sort of the control flow graph. We probably want to indicate what the statement is at each node. So at this node, we have some variable w equals x. At node 2, we have w is incremented. So these are the statements you can imagine in your program. And at node 3, we have w equals 2 times w. And at node 5, we have x is 5 times y. At 4, we don't have anything. At 6, we have x equals 6 times y plus 10. And let's see, there's one more. And last one is z equals x plus w. So these are just sort of statements in your program that are represented through nodes. And let's add our conditions. So this happens when some variable m is greater than 0. This is like, the opposite, so that would be less than or equal to 0. And again, you don't always have to label everything, because sometimes it's implied, right? If that's greater than 0, that one is the opposite of that. And then over here we have, let's see, this is if y is greater than or equal to 10. And, or this should be less than. And that's about it. And again, we can label this, but it's implied that that's greater than 10. So now we know our nodes, we know our transitions, the conditions that are required for transitions between nodes. I want you guys to take a shot at what the corresponding code would look like. And maybe I can erase this. Does anyone have ideas? This is messy. So take a few minutes, think about it, and maybe try and come up with the corresponding code. Anybody online have ideas? Anybody? So we're going to go from this control flow graph to code. Yeah, so exactly. So we're going to start, so that's our graph, and we're going to have, that's our starting statement. That's pretty obvious. Then what?
Then you have a conditional, if you need a conditional listed, and then just anything else.
Yeah, so you would have if m is greater than 0, what would you do if m is greater than 0?
W plus plus.
Yeah, so you would do w plus plus, Otherwise, you would have, what would you have?
W equals 2 times W.
Yeah, so W equals 2 times W, and let's label these just for simplicity. So that's node 1, this is node 2, that's node 3. All right, then what?
Then another if statement for the Y conditional.
Yeah, so then we have, we have if else, then we have another if. We have if Y is less than or equal to 10. Then we do basically node 5, which is X equals 5 times Y. So I think you guys can sort of see the pattern, right? You look at the statement that's at your node, and then you look at the transitions, and so you can translate it into conditional statements and so on. So then we have that. Otherwise, we have X equals, what happens at the statements isn't that important, really. We're just interested in the flow and translating it to code. Otherwise that, and then what's the last thing? Yeah.
You have your Z equals X plus W.
So would that be in a conditional or no?
No, because they both.
Yeah, and there's no sort of transition there. So that's something that happens regardless, right? Similar to like a return statement or something. So you would have Z equals X plus W. Okay, so any questions on that? Should be straightforward. I do have one question for you guys. Let me label these. That's 6 and that's 7. Is there more than one possible way of writing the code for this control flow diagram?
Yeah, you could have done the if statements like the other way.
Yeah, so right now we have if m is greater than 0, what we could have done is m is less than or equal to 0, and then replace this with node 3, and then move node 2 down here, right? And then we could do that for this as well, or any combination of those. So the takeaway is that your control flow diagram won't always map one-to-one to, or rather, there's more than one possible way of writing the corresponding code. So yeah, that's just a little observation there. Any other questions? Anybody online have any questions, comments? Looks like it's clear. So the next thing is, I wanted to talk briefly about node, edge, and prime path coverage. So essentially node coverage is, you want to cover all your nodes. And we said that nodes typically represent statements, right? We have all of these statements, not the ifs, but the stuff where you increment a variable or update it or something. Those are typically your statements. And so if you're saying you want to achieve node coverage, essentially what you're saying is you want to achieve statement coverage, right? So node coverage is pretty much its statement coverage. Then you have this idea of edge coverage. And anybody know what edge coverage is equivalent to? So if nodes are statements and node coverage corresponds to statement coverage, what is edge coverage then?
Branch coverage.
Yeah, it's essentially branch coverage, right? Because your edges represent the transitions between nodes, which are your conditions in your program or your branches. So essentially, edge coverage corresponds to branch coverage. And then there's one other thing that's actually mentioned in your assignment. So it's called prime path coverage. So it's kind of a weird concept. Basically, the idea is that, well, first of all, you have to understand the idea of a simple path. So essentially, a simple path from some node I to j is essentially a path where no node occurs twice, except possibly the first and last node. So for example, in this program, I don't think you can actually go back because there isn't like a loop or anything. But you can imagine if you have a loop, you can potentially go to the same node multiple times or some set of nodes multiple times. So that wouldn't be a prime path. So for example, if you had like 1, 2, 2, 3, 3, 4, that's not a prime path because you're visiting node 2 and 3 twice. What would be a prime path though is if you visit each node once, except though the first and last node. So you could potentially visit 1 and 1 twice. That's okay because that's the start and finish. But as long as every other node is visited just once, that's a simple path. And then a prime path is essentially, it's a simple path that is not a subset of any other simple path. So what that means is, what's a subset of this? What's an example subset?
1, 0.
1, 0? Well, there's no 0 here.
you go 1.2.
Yeah, that would be a subset, right? 1, 2. So if that was your simple path, this would not be a valid prime path because that's a subset of this. Okay. So basically, a prime path is essentially any simple path that is not a subset of any other path. So if you look at your assignment, he gives a better example. And I don't know if you guys have your assignment in front of you, but essentially gives you a number of simple paths, and then you can imagine because prime paths are simple paths that are not subsets of other simple paths, you're going to have fewer prime paths than you have simple paths. So anyways, that's sort of the terminology and the definition of a prime path. And then for the assignment, you essentially have to list some prime paths and sort of state the conditions for achieving 100% prime coverage, prime path coverage, node coverage, edge coverage. Any questions about that? It's relatively straightforward. Anybody online have questions? Everybody's good? Okay. So there's one other thing I wanted to talk about, which also relates to the assignment. So here's this. It's really dirty. So on the last question, there's, or I think the second or third question, one of them, it talks about sort of taking a given program and partitioning it into what's known as characteristics and blocks. And it's not very clear what that is exactly. So essentially, you can imagine you have a program and you want to test it, but there's many different possible inputs that you could provide it, right? So you want to sort of have a more, a mental model of your sort of input space. So you want to sort of group your potential inputs to the program into general categories. So you can imagine if you have like a, validate email method, you want to test it, right? So you might divide sort of your test inputs into valid emails and invalid emails. And then, so those will be considered your characteristics. And then you might want to divide that further into, okay, what's an invalid email? There's different types of invalid emails, right? Maybe it's missing the @ symbol, maybe it's not the right length, maybe it's missing a special character, maybe it doesn't have the .com or something like that. So you want to divide sort of your possible inputs into further, categories essentially, and that's referred to as a block. So we'll do an example in a second. And then you can also have invalid email, or you can have valid emails, and you can have different types of valid emails. So you can essentially keep dividing your input space to sort of get a better mental model of all the possible test inputs. So the example I just mentioned is, let's say you have an isValid email method, and let's say that takes a string. So let's say it takes a string email. We'll just sort of describe this in pseudocode. You can say that, well, email is not null. That's one of them. Then you could say email.length is greater than 0, can't be an empty string. What else? So you could say that it contains, contains the @ symbol. You could also say it contains, the .com, or maybe .ca, or whatever you want to add to that, .uk or whatever. Then you might also have, a length requirement. So you could say at least 10 characters, or you can describe better. You can say email.length is, or actually, let's just add that there. Length is greater than 0, or maybe we can say 10. You need at least 10 characters, right? So you have a number of different conditions that you're going to use to validate emails, right? So that's sort of the pseudocode for this, and then you want to come up with the characteristics and the blocks that sort of partition your input space when you're testing this. So let me erase this, and we'll do that. So a characteristic is essentially, it's a high-level description of what exactly you're testing. And then below a characteristic, you have a number of blocks. So you have block 1, block 2, and we'll talk about what these mean in a second, and so on. So the characteristic might be, and the characteristic is generally like a high-level description of what the particular inputs are going to look like. So blocks essentially describe certain inputs or types of inputs, and the characteristic is more sort of a high-level description of sort of capturing what those inputs mean. So a characteristic might be, test valid emails. So you're going to just test the valid emails, and then you're going to describe each possible input in blocks, right? So you might have, we said that a valid email meets all of those conditions, right? So you might have something like John Doe at gmail.com or something. That's considered a valid email. And actually, typically, you don't pass an actual test input. It's more of a description rather than a precise input. So this would be something like, block 1 would be test not null, for example. So because that's one of the things that a valid email is, it's not null, right? Then your block 2 might be that length is greater than 10. And so you can sort of keep going and figure out what your valid emails are. And there's 2 important properties to keep in mind when you're doing these characteristics in blocks. Basically, 2 properties are completeness and disjointness. So completeness is easy. It essentially refers to capturing all the possible inputs. So right now, is this complete or no? Why not?
There's like other requirements.
Yeah, like we said that these are all the things that a valid email is. It's not null, it's greater than 10 characters, but right now we only have 2 blocks. So we didn't capture this last requirement, right? So right now this isn't complete. So again, completeness just refers to capturing all the possible types of inputs that you could pass for this particular characteristic, right? And you can imagine if this was test invalid emails, you would have sort of the opposite of these, right? And you'd want to capture all the possible types of invalid emails. Then the other property that you want to have is disjointness. So this one's kind of complicated, to wrap your head around the first time, is essentially what you want to do is, no 2 blocks should, like each block should capture or test something unique. So essentially you can think of it like, if you have a test input that could fall under more than one block, then your set is in disjoint, right? So essentially you want to be testing something unique with each block. So what that means is, let's say you're testing invalid emails. Test invalid email. So separate this. So that might be another, and this would be another characteristic, right? So you have test valid emails, then you have another characteristic for testing invalid emails, and then you're going to have a block. And we said that a valid email is not null, so you might test with, null email if you're testing invalid emails, right? So you're doing the opposite. And then you might test with one that doesn't have the @ symbol. And then you might test with, let's say, so you might test with one that doesn't have an @ symbol, but you might also test one that has length less than 10. So you could do, length is less than 10. Would this be disjoint? Or in other words, is each block testing something unique? Or even better way to think of it is like, is there certain inputs that could fall under more than one block? So one block, 1, 2, 3. So is there a test input that you could pass to is valid email that could be categorized under more than one block? Yes? I see you're shaking your head.
Yeah, because like you could have it length less than 10 and not.
Yep, that's exactly the point. These 2 are not disjoint because you could have something like, let me write this over here. You could have something like, John.com, right? So that has length less than 10, and it also doesn't have the @ symbol, so that's not a valid email, right? And this, these set of blocks are not disjoint because they don't test, because there is an input that you could pass that exercises more than one block. So what he wants you to do in the assignment is he gives you this example of, I think searching like a list or something and describing the characteristics in blocks. What he wants you to do is essentially describe the blocks in such a way that they're disjoint and complete. So complete is easy, you just need to capture everything. Disjoint is slightly harder, and really it just comes down to your wording. So if we wanted to make this disjoint, how could we do that?
Would you like combine the blocks? Or?
Oh yeah, that's one way. But it really comes down to wording. So you could just word this differently. So how could you reword this so that it's disjoint? Well, you could reword block 2 to say it doesn't have at, but the length is greater than 10. And then for block 3, you could say that the length is less than 10, but it contains an at and .com and so on. So that it only exercises one particular scenario, right? So that if you pass an input like this, it only falls under one block. So that's the idea. So you could say it doesn't have at, and I'll say L for length is less than 10. Sorry, greater than 10. Yeah, greater than 10. So then when you pass this input, and this says doesn't have at, yeah, so when you pass that input, that only falls under this block, because this block specifies that you can have inputs that are of length greater than 10, and they don't have at. So now that possible input falls under only one block, so this is considered disjoint. So any questions on that? It's kind of a weird thing to wrap your head around initially.
Would no count as having like less than 10?
That's a good question. Yeah, I mean, I think you could argue either way, because, I mean, technically if it's null, it doesn't even have a length, right? So you could say that, or you could treat them the same. It's not a big deal. Yeah, any other questions? Anybody online? Chat's been quiet. Don't think there's any questions.
So the only way to get around having a disjoint is by making sure that only other blocks conditions like block exempt will be violated.
Yep, yeah. So I think the assignment example is like a search method, right? And then you might have certain blocks that correspond to finding an element, let's say at the front of the list and the back of the list. But then maybe what if you have a list that only has one element, right? Then those two blocks overlap because the first and last element are the same. So that's just, I don't want to give away the whole answer for the assignment, but that's just one example of how this corresponds to the assignment, right? So other questions? So you came just on time because our lesson is over. So yeah, that's all. If you have questions about the assignment, I'm happy to answer. But yeah, relatively quick and straightforward tutorial today. So yeah, that's all. And I'll stop the recording.